And thanks again for everybody for registering and showing up. This is our second seminar talk in the Center for Quantum Networks seminar series that will keep on going here. So our first few talks, as a lot of you know, are meant to be kind of a general overview of the different disciplines and topics that we deal with here at the center. And then we'll start to get into more technical talks as this goes along. So first I want to introduce Dr. Saikat Guha. He's going to be giving the talk today. So he is an associate professor at the University of Arizona, and he is also the director for the NSF Center for Quantum Networks. His background lies at the intersection of information theory and optics. His interests lie in investigating fundamental quantum physics-driven limits on photonic information processing, which has a lot of applications. And he is also interested in network science, and he'll be discussing some of that with us today, specifically quantum networks. So, Saikat, the show is yours.
All right. Thank you very much, Russ, for that introduction. And thank you for coming to this second talk in the CQN Education Workforce Development Seminar Series. Russ, if you could please confirm that you see my full screen on PowerPoint.
Yep, you are good.
All right, thank you very much. So as Russ said, I'm a professor with the College of Optical Sciences, jointly appointed with the ECE and the Applied Math departments. We are going to talk about the Center for Quantum Networks today. So, this is a newly instituted National Science Foundation Engineering Research Center, and this will be a second talk in the series. The first one was given by my colleague Mike Kramer from University of Oregon. And today's talk will be about quantum networks and the role that the Center for Quantum Networks is going to play in developing the full stack technologies necessary to develop and build towards a quantum upgraded internet. So what I decided to do for today's talk is to include some very basic fundamental material building up to our understanding of quantum information. And then I'm going to transition pretty quickly towards the middle of my talk to some real research and technology development that we'll be doing spanning the entire center's research. And hopefully in some of the subsequent talks in this seminar series, we can go deeper into each one of those individual research topics at different levels. All right, so let's get started. So let me get started with this cartoon of the quantum internet. The way our team here envisions the quantum internet is the internet as we know it today that has been upgraded to enable a new service. And that new service being the internet's ability to communicate, transmit qubits, which are the digital equivalent of quantum information that is sent with high fidelity and high rates on demand to support multiple new applications that might benefit from that service. You'll hear about some of these applications both in my talk later today and in some subsequent talks, hopefully in the seminar series. One of the biggest things about this new kind of service is that the qubits are much harder to send compared to bits. They are much more fragile objects. The rate at which you can send qubits decays exponentially with the loss in optical fiber. And there's no way to amplify that using standard optical amplifiers as we are familiar with in the current day internet. You have to design instead something called the quantum repeater in order to circumvent that exponential decay of rate versus loss. One has to build the quantum internet in a way that various types of hybrid qubit-based technologies, such as color centers and spins, superconducting processors, trapped ion-based quantum computers, and many other quantum processing technologies that are being developed by the community right now, is able to hook up to that quantum network, is able to leverage and benefit from that service. So one has to build converters that can go from a photonic qubit to one of these memory processor qubits. By the way, one of the things I should say right at the outset is that there is really no alternative to photonic way of encoding that qubit for long distance transmission. That's really the only form of carrier or bearer of qubit that can fly long distance without being corrupted really badly. On the other hand, in terms of processing quantum data, there are other contenders that might be better at doing the job. So anyhow, so this is just a cartoon of the quantum internet. What I'm going to do is that step back and talk a little bit about what qubits are, how do we do computing with them, what does it mean to send qubits around, and what can we do with it. Okay, so that's the plan for today's talk. These are the partners that are part of the Center for Quantum Networks. The University of Arizona is the prime lead organization. We have MIT, Harvard, and Yale as what NSF calls the core partner institutions, and several other universities here: Northern Arizona University, UMass Amherst, Howard, University of Oregon, and BYU, and University of Chicago, who are partners on CQN as well. This is an incomplete list of an industry. I meant to update it. This is not updated. We have a few more industry partners who have joined since we wrote the proposal. And we have members from the leadership teams of several leading international centers researching quantum networks on our external advisory board. So let me start with some very, very basic fundamentals. And some of these will overlap with Professor Mike Kramer's talk in the first talk of the series, but hopefully this will be a booster for some of the topics that you saw that Mike presented. So a qubit is you can think of a qubit as a superposition of a 0 and a 1, where the 0 and 1 are two unit vectors, two column vectors that are orthogonal states. So think of 0 and 1 as two orthogonal vectors, and a qubit is a complex valued superposition of 0 and 1. So this green line is a state of a qubit. That's the state of a single qubit. So as you can see, the state of a bit that we are used to in classical computing and communications can take 0 or 1, whereas a qubit can be in any superposition of a 0 and 1. So it's a generalization of the concept of a bit. One of the important things about a qubit that we should notice that the qubit can be represented in any orthogonal basis. So if I define two states plus and minus to be an equal superposition of the 0 and a 1 with a plus and a minus sign, you can rewrite that same state in terms of two different complex numbers that are gamma and delta, that are superpositions of plus and minus. But the important thing is that for a qubit has to be a unit norm vector. So it's an alpha and beta. Unit norm vector just means that magnitude squares of alpha and beta add up to 1. Since alpha and beta are two complex numbers, a little bit of thinking, very basic linear algebra, it tells us that this unit norm vector can be thought of as a unit length vector inside a unit sphere, inside what is called a block sphere. There are two parameters, two phases, theta and phi, that completely characterizes a general state of a single qubit. So any point on the periphery of that sphere corresponds to a state of a qubit. So one thing you should see right away is that a qubit is it's a continuum object. Okay, even a state of a single qubit can be any point on that surface of that ball, that unit radius ball. We are all used to gates for classical computing. So when you think of, if you open up your computer and look at how logic is performed, you see things like NOT gates that flips a bit from 0 to 1 and vice versa. There's something called an AND gate that produces an answer and takes input of 2 bits, and it produces a single bit answer which is only 1 if both of the inputs are 1, and so forth. In quantum computing, a qubit, a gate on a qubit, you can think of that as a rotation. You take a state of a qubit, and if you rotate it by a certain angle, that's doing a gate on that qubit. Mathematically speaking, that rotation on a single qubit can be thought of and represented as what is called a unitary matrix. A 2x2 unitary matrix U is such that U dagger U is identity. U dagger is what is called the Hermitian conjugate of the matrix. You take the 2x2 matrix, transpose it, and make and complex conjugate every entry. That's the unitary, that's the U dagger. So there are many unitaries you can do on a single qubit. These Pauli matrices, X, Y, and Z, are 3 favorites of quantum computing theorists and engineers, and you will see some of them later on today. This Hadamard gate is a special kind of a 1-qubit gate that takes the 0 state and the 1 state and rotates them into the minus state and the plus state respectively. All right, let's talk about a 2-qubit state. So a single qubit can be any superposition of 0 and a 1, the two states of a single bit. 2 qubits can be in any arbitrary superposition of the 4 states 2 qubits can be in. So two bits can be in one of 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. So 2 qubits can stay in any superposition of these 4 states. What it means is that the state of 2 qubits is described by this 4-element column vector whose magnitude squares of these coefficients have to add up to 1. Now, if I take a state of a qubit A, let's say this is the state of qubit A, and this is the state of qubit B, and I bring them together and say, I want to write down the state of the 2 qubits. I'll say, okay, qubit A is in this state and qubit B is in this other state. But I can represent that as a superposition of these 4 states where the coefficients will be products of the coefficients of the individual coefficients that represent the states of the individual qubits. And it's easy to verify. You can do it very easily that if the magnitude squares of these A0 and A1 add up to 1, and the magnitude squares of B0 and B1 add up to 1, then the magnitude squares of these 4 things will add up to 1 as well. These states are called product states, meaning I can talk about the state of the qubit A and state of qubit B independently. They're just 2 separate entities, two separate states. On the other hand, I can come up with values of alpha, beta, gamma, and delta such that writing the state of the qubit in this particular form, a product state form, will not be possible. And the simplest example of that, is that state over here. So alpha, let's say, is 1 over root 2, and delta is 1 over root 2, but beta and gamma are 0. If you do that, then I cannot take this qubit and write it as a product of 2 states of a single qubit. Such states are entangled states. Entangled states and entanglement is a quantum mechanical phenomenon that does not have any classical counterpart. You can think of entanglement as a fundamentally more powerful form of correlation than classical probabilistic correlations would allow. This particular entangled state is also called the Bell state, which happens to be the maximally entangled state of 2 qubits. This is the state that has the maximum entanglement between 2 single qubits. Now, we talked about gates for single qubits as a rotation on that block sphere. Now, when I go to 2 qubits, it's not easy for me to think of another equivalent of a block sphere on which a 2 qubit state lives because it's in a higher dimensional space. But now that we have the tools of mathematics and linear algebra, we don't have to worry about visualizing the state of a 2 qubit. A gate on a 2 qubit state is simply a 4x4 unitary matrix. A 4x4 unitary matrix, meaning U dagger, U is 0, is identity on the two qubit vector space, and U is some unitary matrix, is a legitimate gate that I can do on the 2 qubits. Now, there's one kind of a 2 qubit gate that can be created, that can be written as a controlled version of a single qubit gate. So what I'm calling here a controlled U gate, it means that I take 2 qubits on which the gate is acting. It's a 2 qubit gate notated like that. What this does is that it applies the single qubit gate U to this second qubit if the first qubit is in the state 1. But if the first qubit is in the state 0, it leaves the state of the second qubit unchanged. So only when the state of the first qubit is 1, I apply U to the state of the second qubit. So if I have this is my 2x2 unitary for the single qubit gate, this would be the 4x4 unitary for the 2 qubit gate. Now let's take a very simple example of a control U gate. So let's take a control NOT gate or a control X gate. If you remember from my slide on the X gate for single qubit poly operator, the X gate simply flips a bit. It takes 0 to 1 and takes 1 to 0. So let's start with 2 single qubits in a product state, 0 and 0. They have no entanglement. I apply the Hadamard gate to the first qubit. So I rotate that 0 to a plus, which is that equal superposition of a 0 and a 1. And then I apply this control NOT or control X gate. And notice here is that I would flip the second qubit only if this first qubit is in the state 1. So if this qubit is in the state 0, I do nothing to the second qubit. But when this first qubit is in the state 1, I flip that second qubit state. But then since the first qubit state is a superposition of a 0 and 1, the gate acts coherently on that superposition. So what comes out on the right-hand side is a superposition of the state 0, 0 and 1, 1, which we just talked about. This is that maximally entangled state of 2 qubits called the Bell state. So what we see here is that 2-qubit gates can be entangling gates. You can act a 2-qubit gate on a product state of 2 qubits and create entanglement out of that. This is a very, very important principle to create entanglement. Now, this particular gate is a very popular among quantum computing theorists called the control Z gate. So if I take 2 single qubits in the plus state, and again, a product state, so both of them are in this state. So the total sum, if I were to write down the state of these 2 qubits, it will be just 1/2 0 0 plus 1/2 0 1 plus 1/2 1 0 plus 1/2 1 1. And this gate applies a negative sign to this qubit. It applies a phase to this qubit, a pi phase to this qubit if the state of this qubit is 1. And that pi phase does nothing to the second qubit if it is in a 0 state, but when it is in the 1 state, it applies a minus sign. So what it creates on the right-hand side is also an entangled state. Now, this particular type of an entangled state, this is also happens to be a maximally entangled 2-qubit state. Not quite a Bell state as it is written here, but it is local unitary equivalent to a Bell state, meaning I can take these 2 qubits and apply a single qubit gate on one of those 2 qubits and turn that into the Bell state. I'm not going to show how to do that here, but this particular state is called a cluster state. A cluster state is a very specific type of an entangled state where I prepare individual qubits in the plus state, the equal superposition of 0 and 1, and apply control Z gates to connect them into a larger and larger entangled state. Let's talk about universality for gates. Again, let's go back to classical computing. For those of you who have taken some form of digital computation, you know that any Boolean logic can be decomposed into NAND gates. NAND gate is the NOT of an AND gate in classical computing. Similarly, in quantum computing, if I were to ask you to take a unitary operation acting on a collection of 100 qubits or 1,000 qubits, a general a unitary operator, which could be a large operator satisfying U dagger U equals to identity on the Hilbert space of all of those qubits on which they are acting, you can always realize that unitary, decompose that unitary into a succession of a few single qubit gates and one 2-qubit gate. I'm giving you here one example of such a universal gate set, the pi/4 rotation along the y-axis of the block sphere, pi/8 rotation along the z-axis of that block sphere, and the control NOT gate that we just talked about. So any unitary operation across any number of qubits can be represented, can be broken up into elements from this set. There are many examples of such universal gate sets. Universal gate sets can be different for different native forms of quantum computers. Some quantum computers might be natively better suited to do certain kinds of single and 2-qubit gates, whereas some other computers might be better at doing other kinds of gates. But for a quantum computing substrate to be universal capable, it has to have the ability to do a set of gates, single qubit and 2-qubit gates that are universal. This is how a typical quantum circuit looks like. You start with a few qubits prepared in some initial state. In this case, I'm showing 3 qubits initialized to 0 state. You pass it through a set of gates. And as we just saw, as we pass the qubits through a set of gates, they get entangled. At every point in the circuit, as they go through these gates, the state of the 3 qubits is always writable, expressible as a superposition of the 8 states of the 3 bits. The hope is that the algorithm that we are trying to implement will be so that at the very end, before we make a measurement on these qubits, that the state of this qubit, these 3 qubits, will be such that the coefficient corresponding to those 8 states, that is the answer to the computation, will have the highest probability amplitude. The value of that coefficient will be the highest, so that when I make a measurement and the qubits collapse to either the 0 or the 1 state of the measurement, that I'll get that as an answer. Now, something I must say here, which I skipped when I was describing the qubit, is the notion of a measurement. When I have a qubit that is a superposition of a 0 and a 1, I only get to see the qubit through the eyes of a measurement. When I make a measurement on that state alpha 0 plus beta 1, the state immediately collapses to either the 0 state or the 1 state with probability magnitude alpha squared or probability magnitude beta squared, respectively. I don't get to read off the values of alpha and beta. And if I take that same qubit and make a measurement in the plus minus basis, then my state of the qubit collapses to the plus state or the minus state with probabilities magnitude gamma squared or magnitude delta squared, as I wrote in the beginning. So when you make a measurement on a single qubit, what you see at the end of the measurement is a bit. You only see the 0 or the 1, the eigenstates of the measurement. So here, when you make a measurement on the 3 qubits, you only get to see one state of those 8 possible states in the superposition. So even though the quantum computer is acting collectively on all these 2 to the 3 possible states, you get to see only one state at the end. But the ability for a quantum computer to carry the superposition of these 8 possible states of 3 bits gives it fundamentally more computing power that classical computers that we are familiar with don't have. And quantum computers can solve problems like factoring very efficiently using Shor's algorithm. It is very good at searching through unstructured databases, like looking for marked vertices and objects in a graphically represented database and related problems. There is another model for quantum computing, which is quite interesting for photonic-based qubits, called the measurement-based model of quantum computing, sometimes also known as the cluster model of quantum computing. I talked to you about the cluster state a little bit ago. So let's take a graph. I'm just showing here a square grid. Just take a square grid graph. And you lay a single qubit on every node of that graph. And the qubit you put on every node on the graph, let's say, is in the plus state. That plus, remember, is the 0 plus 1 over root 2, equal superposition of 0 and 1. Once I've laid those qubits at the vertices of the graph, the qubits are in the product state. There is no entanglement. And then I look at wherever there is an edge in the graph, underlying graph, I go and do a control Z gate on the 2 qubits at the endpoints of that edge. And by doing so, I create a cluster state. Now, it just so happens that there is a one-on-one map between a quantum computation in the circuit model that I just described, where you prepare a set of qubits and push them through a set of gates, to another model of quantum computing where you start with this generic cluster state, that I just described, and the quantum computation is simply encoded by a set of single qubit measurements of that cluster state, one at a time, where the measurement basis, the 0, 1, plus, minus, or whatever single qubit measurement basis you choose to measure every subsequent qubit, is informed by the measurement result, that 1-bit measurement result you got as a result of measuring the previous qubit. So you measure column by column by column by column on that cluster state. And at the very end, you are left over with the last column. And one can show, that was shown in this paper by Rausendorf and Briegel, that state is exactly what you would have had at the very end of the equivalent quantum circuit before you made the last set of measurements. And hence, if you measure off those qubits, you would get the same exact answer that you would have gotten in the circuit model of quantum computing. Now, there's this one-on-one map is nice, but then there are certain quantum computers that are good at the circuit model, and those quantum computers are where the qubits are sitting inside a box, kind of like in classical computers, where say superconducting qubits. Each qubit is inside a resonator, and you get to do single qubit gates. You can get to do 2 qubit gates, a set of a pulse sequence, for example. Trapped ion quantum computers are another example. For photonic qubits, the cluster model is very nice because you can create this generic cluster state. And you can think of this cluster state as kind of like a fabric weaving machine, where you weave the cluster from one end and you keep chewing it away from the other end, this measurement of the cluster column by column by column. So you don't really have to have the entire cluster alive at the same point in order for you to encode the computation. And since photons like to fly rather than sit inside a box, this model is particularly suited for photonic-based quantum computing. There are 2 companies that are partners of CQN, PsiQuantum, which is based in Palo Alto, and Xanadu, that is based in Toronto. They're pursuing 2 different forms of photonic quantum computing. One of the biggest advances in the theory of quantum computing was the notion of fault tolerance. And this is a very, very important concept, which is often not talked about as much as it should be. There has been so many models of analog computing back in the day, from through the 70s and the 80s. It was a really big topic of research. Still, there are people working on analog computing. Qubit might seem like an analog concept, and some people might think that quantum computing is like an analog computer, but it's really not. It is much more powerful than a traditional classical analog computer, in the sense that there's a theorem that shows that if the noise level for every single qubit gate in the universal set is below a certain sharp threshold, then there is a way in which you can encode quantum computing fault tolerantly. By that, what I mean is that you can take a collection of qubits and create a logical qubit, and you can enact gates upon those logical qubits such that you can drive your probabilities of error of the computation down to as little as you wish. This threshold theorem or fault tolerance threshold theorem has a counterpart in the circuit model and the cluster model both. Let's talk about a little bit more about measurements, but now measurements on 2 qubits. I talked about measurement of a single qubit being a set of orthogonal vectors that define a basis for the single qubit vector space. So for example, I talked about you can measure a single qubit in the 0-1 basis, which I call the computational basis, or you can measure the single qubit in the plus-minus basis. Plus and minus are 2 orthogonal states that can be used as a basis to write the state of a single qubit. Similarly, if you were to ask what is the most general form of a measurement on 2 qubits, I'll say that pick any 4 vectors. It's hard to visualize 4 vectors in a 4-dimensional space. Any 4 vectors that are orthogonal to each other and spans the space in which a general 2 qubit state lives. Those 4 vectors will define a legitimate von Neumann projective measurement on the state of 2 qubits. So on the left-hand side, I have the computational basis for measuring 2 qubits, which is very simple, constructed out of the computational basis for measuring a single qubit. On the right-hand side, I have 4 vectors that span the same exact vector space spanned by these 4 vectors here. But notice that all of these vectors are actually entangled states. They all are Bell states. They're all maximally entangled states. But these 4 vectors are mutually orthogonal to one another. The measurement on 2 qubits in this basis is known as the Bell basis measurement, or the Bell state measurement, or an entanglement swapping measurement. Many names out there. This is one of the most profound, one of the most popular entangling measurements, joint measurements in the theory of quantum computing. And you will see me talking about that in the context of quantum repeaters in a bit. Now, one of the important things about the Bell state measurement is that if I prepare, let's say 4 qubits, such that these 2 qubits are in one Bell state, the entangled state given by phi plus here, and these 2 qubits are in another Bell state, a 2 qubit maximally entangled state, again, the same state of phi plus. And I take these 2 qubits and make a Bell state measurement on these 2 qubits. Notice that when I make a measurement, the state of the qubit collapses to one of the eigenstates of the measurement. But in a physical measurement device, what really happens is that those 2 qubits are lost as a result of that measurement. So there's nothing left over once you have measured off those 2 qubits. But one interesting thing that happens with the Bell measurement is that since you're making a 2 qubit measurement, you're going to get a 2-bit answer to that measurement, right? You will get an answer 0, 0, 0, 1, 1, 0, 1, 1, 2, 4 different answers corresponding to these 4 Bell states that you projected these 2 qubits onto. Depending upon which measurement result you got, the state of these 2 unmeasured qubits that were originally part of 2 separate Bell states project themselves onto one of these 4 Bell states, depending upon which measurement result you got. And since you know that measurement result, you can apply a conditional single qubit gate on one of these 2 qubits to convert this state into one of the generic Bell states, for example, that phi plus state if you desire to have so. So Bell state measurement is an interesting tool that can take fragments of entangled states, potentially distributed over small fragments over shorter distances in a network. And you can use Bell state measurements or BSMs to stitch together these small fragments of entanglement to long distance entanglement. Now, these rules also generalize to more complicated cluster states. I just talked about a cluster state being something that can be thought of as a graph where I put a plus state in each vertex of that graph and use control Z gates to construct, to do entanglement between those nodes. Let's say I take these 2 cluster states, both of a line topology, and then do a Bell state measurement on these 2 qubits. I will project the remaining 4 qubits into some other cluster state. And there's a whole graphical rule that you can develop. It's a paper that my student Shlesha Patil is going to put out soon, that you can use as a lookbook to figure out how you can build different types of Bell state measurements. Sometimes people call them fusion operations because you're actually fusing two small cluster states into one larger one, or two small entangled fragments into one larger entangled state by doing this joint projective measurement. And there are, if you have a success or a failure, depending upon your measurement succeeds or not, you have different actions that happen on the remainder of the qubits. So the fusion occurs if your Bell measurement succeeds. One of the most popular forms of encoding the qubit with photons is what is called the dual rail qubit, where the zero state of the qubit is encoded by placing one photon in one of two orthogonal modes. For example, you can take one co-propagating polarization, circular and counter-circular polarization modes of a Gaussian beam, and place a photon in one of those two polarization modes and call that your zero state or the one state of your qubit. So notationally, I'm writing the zero state of the qubit as 1, 0 and one state of the qubit as 0, 1. This form of qubit, called the dual rail qubit, one interesting feature of this is that if you were to do gates on this qubit, your gates would only succeed with a certain probability if you were to build those gates using linear optical circuits, beam splitters, phase shifters, and photon number resolving detectors. This is just a cartoon from this paper that we did a few years ago, where we looked at if somebody were to give us a steady stream of 3 qubit entangled states in this line cluster topology. Notice here that these are 3 qubit cluster states, and you had the ability to perform Bell state measurements which only succeed with the probability of success of lambda. Is there a way for you to ensure that no matter whether your individual Bell BSMs succeed or fail, that you would always be still left over with a large connected component of the unmeasured qubits, which are in the middle of this structure that I'm showing here, which you can then use for cluster model of quantum computing. And what we found was a very interesting percolation-like behavior, which has been seen in many, many instances in statistical physics, that for this particular structure, if that success probability was above about 0.64, that all these qubits in the middle would be part of a large giant connected component, which you can then renormalize and use it for quantum computing. And there exists a design of a quantum circuit using beam splitters, single photon ancillas, and photon number resolving detectors, all of which are technology that exists. In principle, you can get a success probability of a Bell measurement to be around 25/32, which happens to be 0.78, which is above that threshold. Anyhow, so with that, I'm going to now make a transition to talk about quantum communications and networking. And I'm going to just start with we have talked a lot about technical stuff, a lot of mathematics and notation. Let me start with a little bit of an intuitive understanding of entanglement. So I'm going to go back to that Bell state for a moment and see if we can understand that by a little story, and then I'll build up our story towards what quantum communication looks like and what kind of research we are doing as part of the Center for Quantum Networks. So let's imagine that there's two friends, Alice and Bob. They live on two distant parts of the country, and they both have this peculiar magical mailbox with two doors. There's a red door and a blue door. And they both go there to there's a postman who comes and puts a little piece of paper in their box with a number 0 or 1 every day, and they go open. They just randomly every morning, Alice goes and chooses to open either the red door or the blue door, and takes that number piece of paper out and writes down the number that she sees in that piece of paper. So today she opened the red door and found the number 1. She puts it down on a piece of paper. Maybe the next day she also chooses to open the red door, writes down, finds number 0, writes it down. Perhaps she tries to open the blue door the next day and finds a number, writes it down, and so on. So every day she does that, and then she writes which door she happened to open, and what bit value she got every day. And synchronously with her, Bob in a different city is say doing the exact same thing. He's opening the red doors and blue doors completely randomly every day. He's not coordinating with Alice at all, and he keeps his record of the door color on his mailbox and the bit value he got. And then once they are done, a month passes, they have 30 bits recorded every day of the month. And then what they do is that they talk to each other about what color doors they opened. Now, one thing they notice is that, so by the way, this is what would happen if magically their mailboxes were entangled, that on the days that they both happen to choose to open the red door, they would both get the answer 0 on their pieces of paper that they found inside their mailboxes, or 1. So the days they open the same color door, the bit values that they found would be completely random, but they would be exactly the same. But on such days where they happen to open a different door, there's no correlation between what values they got. They could have both gotten 0, 0 or 1, 0 or a 0, 1 or a 1, 1, doesn't matter. Could get all 4 combinations with equal probability. But again, if they happen to open the blue door, both of them same day, they would get the exact same answer. So now you can see this. So what they do is that they talk on a telephone and they say that, okay, can you tell me which days you use which door? And they only, they strike off all the days in which they happen to use a different color door. So blue and red, red and blue and so on. And on the days they had this open the same color door, they have the exact same bit value. So this bit value that they get, this is called a secret key. So you can turn entanglement into a shared secret of a form that even if an adversary was listening to their this phone conversation, that she would not be able to tell. She would not be able to get any information about the shared secret that they got. Now, why is shared secret important? One of the important things about classical communication security is that the only way to have provable security in your communications is by what is called the one-time pad. The idea goes back to several decades. Now, back during the World War, people used a one-time pad to communicate really, really highly secure information. A one-time pad means you take a bit stream that encodes your message, you bit by bit add a random your shared key, and then you transmit that ciphertext after you have added that shared key. And then once the receiver gets that ciphertext, he or she adds back that shared key, and then the message pops up back again. The big problem in communications theory is that how do you generate that shared key in a way that nobody else has access to that shared key? It has to be completely random and nobody has to have any information about that. The way we do that right now on the internet is by using what is called the Diffie-Hellman Protocol. The Diffie-Hellman Protocol can enable 2 parties to just talk on a phone line or any classical channel and generate a shared key. They don't have to use entanglement. But the problem is that the security of the Diffie-Hellman Protocol, the fact that an adversary who is listening to that phone line cannot figure out that shared key generated by Diffie-Hellman, relies on the fact that solving a problem called the discrete logarithm problem is computationally impossible or computationally hard by any classical computer. And just so happens that once the quantum computers are built to a certain scale fault tolerantly, that they will be able to solve that discrete log problem with polynomial resources. So the security of the Diffie-Hellman protocol will collapse. Whereas if you have shared entanglement distributed between those 2 parties, then if you use this protocol to generate shared secret from it, it would be provably secure. There would be no way to compromise security of that. Now, this was just a story that I told you, but then that story actually can be realized using that Bell state that we just did a lot of mathematics on. So this was our Bell state, 0, 0 plus 1, 1 over root 2. I'm going to ask you, it's a very, very simple math. You can just re-express the 0 and the 1 state in terms of the plus and minus state. These are the plus and minus states, and you can re-express this state as plus minus minus over root 2. It's the exact same quantum state. So if 2 parties, if Alice and Bob share 1 qubit each of this Bell state, if they both happen to make a measurement in the 0, 1 basis, that is opening the red door, they'll get the same exact answer, both 0 or both 1. And if they both happen to make a measurement with the plus minus basis, they will both get the exact same answer. This is the blue door, either both pluses or both minuses. But if one uses the plus minus measurement, the other uses the 0, 1 measurement, their answers will be perfectly uncorrelated. Let's talk about teleportation. This is a topic that Mike Raymer covered in the previous lecture in this series, but now stated a little bit more mathematically, because now you have the mathematics, underlying mathematics to write it down. So this is the shared state of Alice and Bob. So Alice and Bob, let's say, share a state, this 2 qubit state, this Bell state, and Alice is presented with a new state of a qubit, alpha 0 plus beta 1. And as I said, she cannot read off alpha and beta, because if she just makes a measurement on this qubit, the qubit will collapse to either the 0 and the 1 state if she chooses to measure it in the 0-1 basis. She only intends to send that qubit to Bob. She doesn't care to measure it. Okay. So what she can do is that she can do a Bell basis measurement on the qubit she wishes to send to Bob and her half of the 2-qubit entangled Bell state. And the Bell measurement will give her one of these 4 possible answers. And then she sends that answer to Bob. And based on which of these 4 answers Alice sent Bob, Bob applies one of 4 possible single qubit unitary gates on his qubit. And out of that gate will pop out the same exact state that Alice wanted to send at Bob's end. So this is the simplest form of teleportation protocol. So let's take a pause here and this is an important thing that we should realize, that if the quantum network is working hard to generate entanglement across 2 parties, you can use that entanglement as a resource to teleport qubits. But notice that that teleportation, that act of teleportation, is also consuming classical communication resources. It cannot be done instantly. This classical bit has to fly from Alice to Bob. So teleportation can be done only as fast as light could take to travel from Alice to Bob. And another important thing to note here is that if the quantum network has been architected to transmit qubits as its native service, then you can use it to distribute entanglement, because you can generate local entanglement between 2 qubits and send one of those 2 qubits through the quantum network. So generating entanglement versus sending qubits faithfully, they are 2 sides of the same coin. If you have access to a classical communication resource on an authenticated public channel, you can do either of the 2. So one of the important tasks that CQN is looking at is how should you design the network? Should it be designed to deliver entanglement between multiple parties, or should it be designed to transfer qubits reliably using quantum error correction? For a quantum network, classical bits, qubits, and entangled bits form the 3 most important resources that trade against each other. And you can think of the teleportation as being a noiseless quantum channels version of achieving the point -2, 1, -1. Why is that? Because the teleportation protocol on this noiseless entangled state, it consumes 2 classical bits of communication. It consumes 1 entangled bit, 1 EPR pair, 1 Bell state worth of entanglement, and it generates 1 qubit worth of quantum communication. Any and all of quantum communication protocols that shuffle around bits, qubits, and entangled bits, they can be thought of as different points of the corners, points, and slices of this big trade space between these 3 entities that will fly around in a quantum network. So quantum communications, as I said, is the act of transmitting qubits reliably, but I just explained why this task of transmitting quantum information reliably is exactly equivalent to being able to generate shared entanglement reliably between distant parties, because I can go back and forth between task 1 and task 2. Doesn't matter which one you do, you can do the other. And as I just showed with that mailbox story and the EPR pair, the Eckert 91 protocol can turn shared entanglement into shared secret. So generating shared secret, the task 3 is a strictly weaker task than tasks 1 and 2, which are equivalent to one another, because you can go from the service provided by tasks 1 or 2 and then convert that into shared secret. But just so happens that if you take a lossy optical channel of transmissivity eta, so eta would go as exponentially in optical fiber. So eta is e to the minus alpha L, where L is the length of an optical fiber. The rate at which you can accomplish any one of these 3 tasks is essentially proportional to eta. And this, we proved that in 2014 in this paper, so not that long ago. And it was the actual capacity was figured out by Stefano Pirandola and colleagues in a few years later. It was we proved an upper bound. They actually established the full capacity. Essentially, the qubits per second or entangled bits per second or secret key bits per second, these rates go as proportional to the transmissivity in optical fiber, which goes down exponentially with the length in optical fiber. So this is a big bottleneck for quantum communications. By the way, people had known this for quantum communications for a while, but we just proved here that no matter how you choose to encode the qubit in the photon and design your receiver, there's no way to get around this exponential rate versus distance decay. So the only way to get around this problem is to build what is called quantum repeaters. And this is just a few numbers to show how an exponential decay may occur. I don't need to tell to this audience how bad an exponential decay can be. But one of the things that we should remember is that this exponential decay also stops at some point. The moment you have some amount of noise in your detectors or your systems, your rate crashes to zero after a certain maximum amount of loss. So as I said, a quantum communications network can be designed in a one-way, forward error-corrected way that kind of resembles how classical communication is done, where you take a stream of qubits, encode that into a longer stream of qubits in an error-correcting code. So this longer stream of qubits is an entangled state. Each of the qubits is sent through a quantum channel, lossy, noisy optical fiber, and then a decoder produces the original stream of qubits. So this is called one-way error-corrected forward transmission of qubits. And the other way to generate entanglement is the two-way form, where you generate entanglement across the quantum channel, impure entanglement, many copies, and then you perform what is called purification by acting locally on one side using a quantum processor on all the qubits on this side, and another quantum processor on all the qubits on this side, and exchanging classical data. And you convert many copies of a poor quality entangled state into one copy of a better quality entangled state. So one-way transmission and two-way transmission, they provide the services of quantum communication versus entanglement distribution. And as I just described, the two are operationally equivalent tasks. There has been multiple experiments and demonstrations of point-to-point quantum communications, both for doing QKD as well as actually sending qubits. And this is a set of data collected by my colleague, Dirk England, who is one of the deputy directors of the center. His group has collected painstakingly all this data from all these various papers that demonstrated QKD. And this straight line kind of mimics that line that I showed at the theory plot of rate versus distance in loss in dB. Now, if you insert quantum processing stations along the length of the optical fiber, then your rate is fundamentally limited not by the overall transmissivity, but the transmissivity of the lossiest link. And that translates to, in a more general network, what is called the max flow min cut region of the network, which I'm not going to get into today. So the most very basic form in which a quantum repeater works is that you split up a channel into small segments and you do parallel entanglement generation attempts across small channel fragments. And see here, the red dots are photonic qubits that are entangled with a qubit that is stored in the memory here in a Bell state. This is a Bell state. And the photons fly out to the middle of this elementary link, the small fragment of a channel. They meet in the middle. A photonic Bell measurement is performed on the red qubits. And then if I'm sitting at this repeater node, I get this information back about which of these channels or attempts succeeded or not on the left and the right. And then depending upon the successes and failures, I take the first success from the left and the first success from the right, and I identify the corresponding blue qubits whose entangled pairs successfully entangled themselves with their neighboring red qubits. And I perform a Bell measurement among those blue qubits locally. All the repeater nodes do the same thing. And when all is said and done, at the end of every single time slot, if all these Bell measurements succeed, then you get one long fine end-to-end entangled state. So Alice's qubit here and Bob's qubit here get entangled in an EPR state, in a Bell state. When you work out the mathematics of this, you can show that your rate versus distance decay can actually go sub-exponentially with the length of an optical fiber. This is a very rudimentary way in which you can build quantum repeaters. There are much more advanced ways using error correction and so forth that we are developing as part of CQN. The big breakthrough that happened in our center was led by Professor Dirk England, Michel Lukin, and Marco Lonkar's collaboration in the Boston area. Mihir Bhaskar was the first author in this paper that was published last year. They were able to break that repeaterless communication bound that I showed using a single node that has a quantum memory, which has an ability to do asynchronous Bell measurements, meaning being able to load a qubit from the right and load a qubit from the left at different times and being able to perform a Bell state measurement, a BSM, on those two qubits. This is the most important technological ability that is needed to build scalable quantum networks. And that was the first time this was demonstrated using what are called silicon vacancy color center based memories. These are spin-based qubits, a state of a spin of a single nuclear spin of a defect in diamond can store a single qubit. And you can read that qubit out by using a photonic state that interacts with a cavity that is holding that qubit, where the cavity's reflectivity is dependent upon the state of that spin. In more recent work, this is a theory paper we just put on the archive just a few days ago, in collaboration with Ido Vax and Norbert Linke, we developed a repeater architecture that uses trapped ion qubits, which is another contender qubit that can be used to build quantum repeaters. You can mimic the action of qubits using the cluster states, the same kind of cluster states that I talk about. You don't actually need a physical quantum memory. If you are able to build large photonic cluster states that can mimic the action of a quantum memory by providing error correction against loss seen as a quantum error mechanism. I said a lot in this sentence, but you can read this paper here that describes how a memory's action can be mimicked by an entangled state that acts as a code for correcting errors. The nice thing about this form of a repeater is that you don't need a memory. You don't need to interconvert between the qubit form and the photonic qubit. You can just have photons fly from end to end and deliver entanglement at a rate that exceeds that repeaterless bound. But it is hard to build because photonic cluster states are difficult to realize. These are the results. You can show that this is the direct communication rate, entangled bits per mode. And this is the rate achieved by this all photonic repeater with different numbers of nodes inserted along the length of the fiber. So at any given total end-to-end length, there is an optimal number of repeater nodes that should be inserted, no more, no less. If you insert too many, you can have too much loss. If you insert too few, then your length of your fragment, your channel segment is too high, too lossy. So there is a sweet spot. Error correction underlies various parts of our research. Error correcting within a quantum computer, error correction for generating cluster states that provide error correction to mimic the action of a quantum memory, and both error correcting codes as a mechanism to go back and forth between the qubit in the memory and qubit in the photon in a fault tolerant way. There's a lot of research on different types of materials and devices. We have already talked about quantum memories using these spin qubits. A big part of our research involves developing the spin photon interface. How do you go back and forth between that photonic encoding? I only talked about the dual rail encoding. There are also what is called the GKP encoding, which happens to be the most loss resilient form of encoding that our colleague Liang Jiang is part of the center who developed. How do you go back and forth between different forms of photonic encoding that is suited for quantum communications to the native form of the qubit that is doing the computation or the storage? Detectors and transducers, a big part of our research. Carl Berggren, MIT is a detector expert. He's working on that. Prineha Narang at Harvard working on the theory. Ryan Camacho working on various nanophotonic materials. Tina Brower-Thomas at Harvard University working on diamond growth. Marco Lonkar working on the spin photon interfaces. So all brought together, the network node of a quantum internet is going to have memories, spin photon interfaces, entanglement sources, and some form of a classical communications and computing capability. And then the kinds of questions that will come up is how do you decide on the actions? Like what bell measurements should you perform locally based on your knowledge of what the communicating parties want, what kind of entanglement they want, where they are. And you can show that the network can be used to deliver entanglement at a rate between two parties that exceeds what can be done with just building a repeater chain along the shortest path. So there is a lot of interesting network theory that comes in here, and collaborate with experts like Professor Don Tousley and Leandro Stasilos, who are experts in classical network theory and did a lot of work in the early days of TCP and IP for the classical internet, who are also part of our center. I will not go into too much detail on entanglement distribution, but there's a lot of work we are doing on routing and supporting different forms of entanglement flows, supporting different applications, utilizing not just bell measurements, but GHZ state projections that act on 3 qubits or 4 qubits at a time within a network node that have some fantastic properties that can lead to entanglement distribution in certain regimes of operation that do not even decay with distance. These are very, very recent results, and we are looking at there's a lot of work to be done in this whole area of entanglement distribution. And not just distributing entanglement, but allocating resources to different applications, how do you schedule different flows? How do you manage the network? How do you do tomography of the network? How do you decide where to place the repeaters? And how do you build the entire network protocol stack that can coexist with the protocol stack that underlies the classical internet. So this is the CQN program is split into 4 thrusts. Thrust 1 looks at the architecture. Thrust 2 looks at designing the repeaters. Thrust 3 is about devices and materials and fundamentals. And Thrust 4 is probably the most unique part of CQN that involves a wide variety of researchers, some of who are in the audience today, who are experts in technology and policy, law, economics, social behavioral sciences, who are studying the long-term societal impacts of the quantum internet and associated applications, some of which we may know or perceive today, and some of which may not even know what kind of impact it may have on society. Just imagine, being able to future-proof security and privacy, and what kind of new implications of biases that may come about in a quantum-powered big data processing across the quantum internet and so forth. One of the applications of a quantum computer is the quantum internet is that it will enable any user hooked up to the quantum internet to be able to submit a job on a quantum processor on the cloud in a way that the owner of that quantum computer cannot know what you computed. What are the implications of putting such a powerful technology in the hands of everybody who can use it in a way that you can even fundamentally not know what its implications are? So anyhow, so this is a big program, and this part of the thrust is run slightly differently than the rest of the program. This is run through the Quantum Society Fellowship Program led by my colleague Jen Baumbauer, who is our second deputy director. So she and Dirk England, they both lead different parts of the center's work, and I'm happy to tell you more about that. Through my talk, I already talked about various applications. This is just a list. Entanglement can be used to enhance sensors that are separated long distances, long baseline interferometry, sensor entanglement locally within the confines of an RF photonic receiver pixels. Pre-distributed entanglement can enhance classical communications, especially when you're operating at radio frequency for low power operation. You can use entanglement locally for enhancing the operational ability of things like fiber optical gyroscopes, beam tracking for atomic force microscopy, laser Doppler vibrometers, quantum radars, and so forth. And then there's this whole problem of taking this whole study and taking it to a network science study, meaning understanding how do you distribute and manipulate complex network entanglement. And this whole area of a theoretical study of large scale entanglement will be funded through a new program that we are kicking off in the summer, to be funded by on the MURI program by the Army Research Office. The problem of distributed quantum computing is a brand new field. When you have quantum computers across the network on the cloud, how do you compile a big instruction on a distributed machine in the most resource efficient way? What kind of entanglement should be delivered so that local processors can only act locally, quantumly, and only classically communicate with other nodes on the network, and be able to still perform a quantum computation across those nodes in the network? So I'm not going to read through the technical material here, but I'll just conclude by saying that I'm really excited to kick off the first year of the Center for Quantum Networks. Really happy to see a lot of our colleagues here and people who are interested in this technology in the center. Please email us. Some of the biggest enabling technology challenges that persist in the whole community and our center are good quality quantum sources of entanglement, squeeze light, entangled photons, high efficiency, high bandwidth, long-lived, universal quantum capable quantum processors and qubit memories, and high efficiency converters going back and forth between various forms of qubits. These are the 3 big technology requirements. We are also working on establishing a new discipline and curriculum on quantum information science and engineering. You will hear more about that on our website in the months to come. So that I'm going to end my talk with just an advertisement of a new endowed chair position we just kicked off to attract a senior professor in the area of quantum systems engineering. And with that, I'm just going to unshare my slide and take any questions if there are any.
Oh, and that was an easy introduction.
Saikat, just for the benefit of the crowd, how far away is some of this stuff?
Good question. Depends upon what part of what I talked about. So entanglement sources are quite mature. Spontaneous parametric down conversion, the leading technology for generating entangled photons and squeeze light. We are generating that in at least 3 labs or 3 experiments at U of A, if not more. Multiple researchers in this audience are experts in that. Superconducting nanowire single photon detectors are also very mature technology. There are companies that sell nanowire detectors that can detect photons with efficiencies upwards of 93%. We are working with one of these companies, Photon Spot, to build some of our devices. Quantum memories, I would say, are the furthest behind right now, but I feel that technology is right at the cusp of where a strong engineering push is what is needed to get it to become scalable. The thing that is the furthest behind, at least in my opinion, some of my colleagues may agree or disagree, is interconversion, going back and forth between the photonic form of the qubit and this memory that is holding that qubit in a spin or a superconducting quantum computer. I see, Mike, you have your raise.
Yeah. Oh, yeah. Very nice talk, Saikat. You mentioned in classical cryptography, the Diffie-Hellman algorithm, which is a computer science mathematical algorithm. You said that was virtually impossible to be broken by digital computers, classical computers. But isn't it the case that that's not a provable statement? You cannot mathematically prove that it's impossible in an efficient way. So there could be some brilliant mathematician out there who knows how to crack Diffie-Hellman, and we just don't know that.
That's an excellent point, Mike. So what Mike is referring to is a big dilemma in the entire field of complexity theory, actually. So I'm not a computer scientist. I have a good friend who is a complexity theorist. And he says that there is nothing that is known in complexity theory. They're all full of conjectures. So this problem of factoring, that we know that there exists an algorithm that can solve factoring with a quantum computer in polynomial time. It is not known that factoring is impossible to be done on a classical computer. It is believed to be so because mathematicians have tried for hundreds of years and have been unable to find an algorithm that can do it. On the other hand, there are some applications, some algorithms where there are clean separations known between the classical power and the quantum power. And most of those examples happen to be in search-like problems. And there, quantum provides what is called a polynomial speedup. So for example, if I have an n-bit problem, a brute force search will take you 2 to the n attempts, looking through all the possible things, all the possible values. The best known classical solution might get you a solution, or best possible classical way to solve it might solve that problem in, say, 1.4 to the n time. Whereas there might exist a quantum solution that might solve it in 1.1 to the n time. So there are results like that that are known, but those exponential speed up ones are really the most attractive ones, and some of them we don't know that a classical solution doesn't exist. Very good point, Mike.
It looks like there's a question in the chat from Benjamin. It says, what are the uses of long distance networks other than QKD? And then he just kind of follows up. As far as I know, local networks are sufficient for quantum computation and most other applications.
Okay, very good point. So let me answer the first question first. So I did not spend as much time on my application side. I probably should have, and maybe we should do more talks in the future, Russ, focused on some of these specific applications. I know that, for example, Mike is interested in one of these distributed entanglement-based VLBI problems, and maybe we could have a talk on that topic. So distributed entanglement can enhance sensors that are trying to work together to estimate some parameter that might be a function of the things they're seeing locally, that might be part of a big correlated field. Think of the multiple LIGO interferometers across the world who are trying to look at some far object in the universe together, working together. If you supply entanglement to those telescopes, those LIGO locations, they can work together in a way that is fundamentally superior to them just collaborating classically. Entanglement is the only way, long distance entanglement, for you to be able to submit a job to a quantum computer that is on the cloud in a provably secure way. So that is an application that often people term as blind quantum computing. You are submitting a job to IBM's quantum computer on the cloud in a way that even they cannot read what you're computing on it. You cannot do that if you don't have shared entanglement over long distance. You can use entanglement for enhancing classical data communications in a very specific regime, long wavelength, low transmitter brightness. If you're constrained to that, you can get factor of 10 or more improvement in your classical communications capacity. So there are more applications like that. Distributed quantum computing is another big example. You want to have small fragments of quantum processors at different locations work together as one giant quantum computer. The only way that can happen is if these locations can communicate using qubits.
Real quick, I want to give people a couple more minutes to think about questions. We should wrap up pretty soon here just for respect of everybody's time. But while people are maybe thinking, I do want to just let people know about our next talk, which will be on June 22nd. So next month, it'll be at the same time, but it will be on a different day. So it won't be on a Friday. Off the top of my head, I believe it's a Tuesday for the next one. And that talk will be from Jane Bombar. As Saikat mentioned, she is the co-deputy director of the center, and then she's also a professor of law at U of A. So she will probably be giving a talk about societal impacts of quantum networks.
Thank you very much, Russ, for organizing this series.
And thank you. It's a great talk, Saikat. And if nobody has any last questions, I think we're going to wrap things up here, and we hope to see everybody next month. Oh, by the way, I will be sending out a quick survey, and there'll be some information about this going on YouTube, and so you can watch again and share it with others.